Yeah, hey buddy. Thanks for joining my session. My name is Ken Obata, and first of all, thank you for organizers, sponsors, and volunteers of this event. It's so great to be here. Thanks for having me. Okay, let's start. So my talk is about deduplicating common crawl at scale. First of all, a little bit about me. I'm a senior software engineer currently working at Lyft. I have more than 7+ years of industry experience working on mostly on big data and the data infra at companies. Currently at Lyft, and previously I also worked at the Amazon and KPMG. This near duplicate text deduplication is my independent research project outside of my work, but I hope you will enjoy it. Fun fact, I recently became a dad of a 4-month-old baby, so I'm stressing myself with working and being a dad at the same time. I linked my PyPy page in this slide, but I'll share the slide deck in the Discord channel, so you can find it later as well. Cool. A little bit about the audience. I wanted to understand. This will probably intersect both engineering and science domains. So any of you from engineering background, raise your hand. And science, okay, or other or management layers. Okay, so I can see there both engineering and science people from two different backgrounds. So I'm trying to keep this contents intersection of the two, so that you can at least enjoy some of the parts. So what this talk is about, it's about near duplicate detection Spark library that benchmark results showing that 2.5 billion common crawl documents deduplicated in 4.5 hours under AWS cost of $620. Techniques are used called partition-aware MinHash LSH and partition-aware union find, and I'm going to also explain the design of composable language architecture. The contents, I'll start with the problem setting first, so that I can introduce what exactly is the problem. And then the architecture. Third is about benchmark and how to use the library. Fourth is about design of composable language architecture. Fifth is more about my learnings and what broke at scale, some of the optimization tips. And then I'll keep the last 5 minutes Q&As, right? So the problem, there are 4 subtopics, why it's important, but why it's so hard, what are some existing tools, and then what are some background terminology to understand the problem. First of all, what does near duplicate mean here? Near duplicate in this context is about the documents that are not identical. Yes. Okay. So near duplicate here means documents that are not identical, but they are almost similar, sharing majority of the contents, like 90%. So here, those 2 examples are extracted from public dataset called Common Crawl. As you can see, these are almost identical, except the domain @mark. So that's the definition of near duplicate. Google actually studied this domain of deduplicating training data makes large language model better. So it's already proven and studied well by these researchers in the past that deduplication of near duplicate text matters for LLM training data quality. Yet these are fundamentally challenging at web scale, and there are 4 reasons. One is scaling problem. So Common Crawl simply contains a huge, massive data set. Even one complete snapshot contains 2.5 billion documents. And then second is about combinatoric explosion. If you try to compare n documents, that will require pairwise comparison, so which is infeasible for billions of documents. Third is about unique, specifically for this near duplicate detection system, you cannot split into batches, because if you try to run it into different batches, you're gonna miss detecting 2 similar documents. that are fall under different patches. So we have to run it all together. Lastly, there's a transitive closure. So if document A is similar to B and then B is similar to C, all of these documents should join in the same cluster, and they should be deduplicated together. So this will require some graph connectivity analysis. All right, so what are some existing tools today? I will pick up 3 kind of like existing tools, and then I will share what are some challenges of each of them. First, we have Spark ML library. So they provide MinHashLSH, supporting similarity join, but it faces scalability challenges, and it can easily face out of memory error as document size grows. And this is because of the shuffling. So self-join on bandhash. I'm gonna explain what bandhash means later in the slides. But anyway, self-join on bandhash can easily shuffle across the cluster, which is facing the scalability challenge. Second tool is from Google. They have a repository called Deduplicate text dataset repository, and this is designed for single machine and Rust implementation. It's no horizontal scaling. Then lastly, we have NVIDIA NeMo Curator library. They provide a GPU accelerated MinHashLSH on tech stack called Rapid. It's fast, really fast, but it requires some GPU infra dependency. For a lot of enterprise users, Spark is still the standard majority of users as of today. So our approach targets teams already running Spark on CPU clusters. Academic background. So these are actually from textbook. It's called MMDS, mining of massive dataset. If you took this course from computer science background, this is a famous textbook. My contribution is how I orchestrate these concepts at scale, but these academic concept is very helpful to understand the background of the problem. So there are 4 concepts. First is called shingling. Shingling is just a sliding window of n characters. So if you have a word called LeetCode, everybody do LeetCode here, right? Yeah. So LeetCode, if you have n of 4, you can split into leet, EETC, ETCO, TCOD, and code. Jackal similarity, I guess this is also familiar to many of you here today, but it's to measure how similar 2 documents are. And then MinHash. Basically, the idea is to hash each single, and then we're gonna keep only the minimum value for each document. We're gonna repeat X times with different random seeds so that we can cover enough parts of the document. In the benchmark, I took 64 sampling for each document. There's a famous formula called probability of MinHash A equal to MinHash B. It's actually equal to Jackal similarity of A and B. Why is this important? Because if you know MinHash value, you can actually compute Jackal similarity without actually computing Jackal similarity. So this is the key. This is going to be the key topic of the architecture in the next part. And then lastly, we have MinHash LSH. It's called locality sensitive hashing. This is the technique to reduce number of comparison for MinHash. The idea is that we're gonna split the X number of MinHash signatures into bands. So assume that you have 64 MinHash values. You're gonna split into 8 bands where each band contains 8 MinHash. We're gonna take hash on top of these 8 MinHash, and then we're gonna call it as band hash. So the idea is that if any of the band hash match, we're gonna call it as candidate pair. So why is this important? Because vanilla MinHash does brute force comparison, but LSH does bucketing, and then after the bucketing, we're gonna compare only within the bucket. So this is gonna significantly fewer comparisons than vanilla MinHash. yeah, if you're interested, the textbook covers more details later. Then now we can go over the architecture. I'll first walk through the architecture and then visual example later. Okay, so we have part 1 and part 2. Part 1 is all about MinHash LSH, and part 2 is all about graph connectivity using the partition-aware union find. Right, part 1, MinHash LSH, we have singling, MinHash computation, band assignment, LSH. These 3 steps are already explained earlier in the slides. So assume that for each document, we're going to take singling, and we're going to take 64 MinHash for each document, and then we're going to split it into 8 bands, where each band contains 8 MinHash. All of them cause no shuffle because it's within the UDF or map partition. So first, this is where the innovation starts, spark partition by band hash. So here, documents are assigned to each partition ID based on the band hash from previous step. This means band hash, the documents likely be similar will collocate in the same partition. And later I'm gonna explain what identity repartition means, but we're also going to apply identity repartition between the partition ID column, which is logical, to physical spark partition ID in this step. So this is the step that causes shuffle once because of the identity repartition. Next step is about local candidate generation. So within each partition, now that we have partition ID, we can generate pairs, document 1 and 2. And we're gonna group documents that share identical band hash in this step. This causes no shuffle because everything's happening within partition. Right, part 2 is all about partition-aware union find to deal with the graph connectivity. So we're gonna start with similarity verification. So from previous step, we have document pair, document 1 and 2. For each pair, within partition, we can estimate Jacob similarity score without actually computing Jacob similarity, as I explained earlier. We only need MinHash in this step. So, and also in this step, we can also drop a candidate pair that is under user-defined config threshold. For example, 90% similarity score. There's no shuffle because it's happening within partition. And then next step is about local union find. Within each partition, again, we're gonna identify the transitive closure. So if document A is similar to B, B is similar to C, all of these documents should join the same class, even if A and C were never directly compared. This causes no shuffle because, again, everything's happening within partition. Now, before we run the global union find, we're gonna do the select distinct pair so that we can drop some dupes. Basically, we just run df.drop duplicates on the document ID and parent ID before global union find. This is necessary because the same partition pair, same pair can appear in the multiple partition. As I mentioned earlier, we're gonna split 64 MinHash into 8 different bands. So a same document can appear into different partition ID. So this is basically to drop duplicate before the last step. And then last step is about global union find. So most of the similar documents are already resolved in the local union find, which means within partition. And global union find is to process cross-partition edges, meaning documents that appeared in multiple partitions with different parents, different local representative. This is only about 10 to 15% of against the input documents. And this causes no shuffle because we're trying to run this step in the single machine. And then finally, we can do the deduplication. Basically, the idea is to join back global union find output to input df. and then this goes one last shuffle because of the join. Okay, hopefully this example will give you more understandable. So assume that we have two documents, purple and green. Each document contains 64 MinHash after a singling step, and then we're gonna split into 8 different bands, where each band contains 8 MinHash values, and we're gonna take a hash on top of these 8 MinHash, and then we're gonna call it as band hash. For each band hash, we're gonna assign a partition ID. So in the example of band 1 from both purple and green, we're gonna assign partition 1, assuming that band hash is exactly the same. But different band partition ID might be different because band hash might be different. Let's zoom in to the partition 1. Assume that we have purple and green has the same exact band hash XYZ. And then let's say we have also 2 more documents joined together because these orange and pink also has exactly same band hash XYZ. So we have 4 documents, and we're gonna estimate Jacob similarity, as I mentioned earlier, without actually computing Jacob similarity, only using MinHash. So this is the only pairwise comparison only within partition. So after estimate Jacob similarity, we're gonna have a score, similarity score for each pairs, and then we can drop any pairs that are under threshold that user defined, such as 90%. In this example, let's say we from 4 documents pairs, we have only 3 of them above this threshold. So purple, orange, and green. For each pair, we're gonna create the graph connectivity. So purple, green, orange. Now we should create one graph cluster because these are identical band hash and above the threshold of 90%. And we're gonna run union find, then pick one global representative. In this case, purple is the final global representative document. So that's how deduplication works. Right, I can go over the benchmark result. So one complete snapshot of Common Crawl contains 2.5 billion documents. The benchmark deduplicated in 4.5 hours under 620 AWS cost. The benchmark result depends on 2 different factors. One is AWS resources, such as number of nodes and executors. Of course, if you invest more resources, the deduplication is gonna finish earlier. And then second is algorithm config, such as similarity threshold. If you tighten the threshold from 90% to 95% or above, that's gonna significantly reduce the similarity candidate pair. So that can end early. In this benchmark, I've used the 90% similarity threshold, and the bottom row of the table, 2.5 billion document count, I've used 63 nodes of AWS X time large EC2 instance that consists of 441 executors. Each executor contains 27 gigabyte memory. Now, how to use the library? It's open source, so you can run pip install distributed curator, and then from distributed curator, you can import the main function called partition-aware deduplicate. And then you just pass your Spark session, input df, name of the text column, and algorithm config, such as number of MinHash, number of bands, and then similarity threshold, and also number of Spark partitions. From the result, you can filter out the Boolean flag called isDuplicate, so that you can filter out duplicated documents. And then the result is you can get unique documents. By the way, I mentioned Common Crawl in the title, but it's just used for the benchmark. You can actually run any data frame with the text data set. I mentioned more details in the PyPy project, so if you're interested, feel free to explore. Okay, fourth is about composable language architecture. The previous architecture section is about language agnostic architecture and approach, but this section is more about how we built it. This is more language specific. There's only one slide in this section. If you look at the language distribution to the top right corner, this is from GitHub, multiple language used, and I'm gonna explain why. So PySpark is used for orchestration layer. It's for API, shuffling, scheduling. Python because that's where users live. But the computation layer doesn't have to be in Python. For example, for MinHash array operation, I've used NumPy, which is backed by C and SIMD. So one instruction process 4 values simultaneously. The same benchmark against Scala took twice longer, actually. And then you might wonder why JVM to Python serialization, deserialization is not, it's actually slower than, it's not affecting the performance. So the context is the bottleneck, where the bottleneck is. The real bottleneck in this deduplication system is in the actual computation of MinHash array operation. So taking advantage of NumPy is actually better than just use vanilla Scala. Second point is about shingling and hashing. Python and C is used in this computation layer. You can write direct MH3 is written in C, so we can directly call C function in the shingling and hashing. And then this can avoid Python object creation in the loop. Lastly, Scala in JVM used in multiple functions such as partition-aware, the local deduplication, identity repartition, union find, a lot of locations. Why Scala? Because it's running inside of JVM, so we can avoid Python serialization, deserialization. For these functions, the bottleneck is in the Python serialization, deserialization part. So for function like these, we can use Scala. Also, another reason is to use the Eclipse corrections. They provide primitive type corrections that can avoid boxing overhead. I will also touch about Eclipse corrections in the later slides. One key takeaway from this slide is the composable language architecture is where the industry is heading to. For example, Poras and DarkDB are kind of doing the similar thing. They both orchestration layer is in Python where users interact, but the computation layer is done by different implementation. For example, Pora's implementation is in Rust. Okay, so hopefully this is gonna be the heavy lifting part of in this talk. 5 is about what broke at scale, my learning, and some of the optimization tips. There are 3 subtopics. One is about data skewness. Second is about understanding the locality chain. And then lastly, how to fit global union find in the driver side. Okay, data skewness. I'm curious if anybody also experienced similar data skewness problem or partition skewness in your Spark experience, if you have. No one? Okay, some of you. Okay, so local candidate generation step calls the fetch paired exception, and then this is due to data skewness problem. It's very common for Spark users, and in my code base, I actually did df.repartition using partition ID, but it didn't help, and I'm gonna tell you the why. So this is because in Spark OSS, df.repartition under the hood is applying another hash called MH3 hashing on top of the partition ID column that is already distributed ID. as a reminder, partition ID that I passed is already done by MH3 hashing. So it's running MH3 on top of MH3 hashing. So for example, if the partition ID column is 42 and df.repartition will apply MH3 of 42, that's gonna return the value which is not 42. This is wrong partition, and it's causing the hash collision. The solution is to apply identity repartition. The idea is to map the logical partition ID column value to physical Spark partition ID. So using the same analogy, partition ID of 42, you can apply identity repartition and then get the 42 to physical Spark ID. So this is the correct mapping correct partition ID that I wanted. I've implemented this identity repartition in the repository. Yeah, so that really helped. So the question is, are we done with the skew? Not yet. There's another problem, and I'm gonna explain deterministic sorting. So what identity repartition solve is the mapping of logical partition ID column to physical partition ID, but what if logical partition ID column itself is skewed? I know that logical partition ID is done by MH3, so it's already well distributed. However, at the internet web scale, there are a few hot partition ID generated from MH3. So that's the problem, and we cannot use ordinary sorting, which is doing the random sorting, because random sorting is gonna split already collocated documents apart. So that's gonna require second shuffling to collocate the documents again. Deterministic sorting, on the other hand, is only sort the hot partition only and use the bound hash as sort key. So this means bound hash is the same, means documents likely be similar is gonna stay together even after deterministic sorting. On the other hand, if you use ordinary sorting, random sorting, these documents that are likely to be similar are going to be apart again. So for example, using the same example, assume that hot partition ID is 42. This is detected by group by count pre-scan. We can split the hot partition of 42 into another 100 sub-partitions. So new partition is gonna be 42 plus, we're gonna take bound hash modulo of 100. And even after the deterministic sorting, bound hash is used in the sort key, so partition ID is gonna be same. So collocation stay together. Okay, second topic is about locality chain. In this locality sensitive system, locality constraints downstream the downstream design. So understand the chain is very important before optimization. For example, df.dropDuplicate, if you remember from the architecture slide, usually best practice in Spark developer is to run the df.dropDuplicate as early as possible, so that downstream layer doesn't have to suffer from duplicated number of records. However, in the locality sensitive system, best practice is not always the best practice. So we can only drop duplicates after local union find, because if you run this df.dropDuplicates, that's gonna destroy the locality even before the union find. So yeah, only after local union find, that's when locality is no longer needed, and that's only when you can apply the df.dropDuplicates. Another example is accumulator instead of df.count. Many people use df.count for any purpose. For example, doing the statistic analysis logging, people use df.count. In the locality sensitive system, And also for this web scale system, we can drop duplicates, as I mentioned earlier, because that's gonna destroy locality. So as a result, DF is gonna tend to be massive, and as a result, we can persist. And as a result, we can run the df.count because that's gonna df.count without persist is gonna recompute. So we needed to use the accumulator as a result. For those who don't know what accumulator is, it's a write-only variable that executors increment. So the driver reads the total result after the accumulation, after the job action completed. So this goes 0 extra stages. Okay, lastly, this is about how to fit global union find in the driver. So as a reminder, the goal of global union find is to resolve the documents that appeared in multiple partitions with different parent ID. And this is only about 10 to 15% of input document with 90% similarity threshold. The baseline solution, what I mean is existing solution, is to run the iterative cycle until all edges converge to one global representative. So using a GraphFrame, for example. For those who don't know, GraphFrame is a Python PySpark library that can help you create graph connectivity. So baseline exists. The problem is the slowness because it reads shuffle data and then writes the checkpoint to HDF. Why checkpoint? Because it's an iterative, as I mentioned earlier. So first iteration is going to write checkpoint to the next iteration and over and over. So that's the bottleneck. The alternative solution that I picked is process all edge in one pass, no iteration in one memory. But the challenge is how do you fit in memory in a single machine? The solution is to run it in the driver side and use Scala. Why driver? Because running on the single executor will increase executor memory at the cost of losing executor count. So there's a trade-off. Driver side has standalone memory, so almost no trade-off. And why Scala? I'm going to explain next slide. There's two techniques to reduce memory and then running global union find on the driver. Two techniques is to first using the encoding from string to long so that we can reduce the memory size. Second is to use the eclipse of long hash map. So these ended up with the 30 gigabyte peak driver memory. Two traps of encoding. First is encode. You cannot use the global sort because it's going to cause shuffle. So use monotonic increasing ID. But monotonic increasing ID is non-deterministic. That means running twice is going to cause a different ID. So we needed to use checkpoint immediately after monotonic increasing ID. No recomputation, no different values. All right, so that's everything I wanted to share. 4 points for key takeaways. Partition-aware system and locality will eliminate shuffles. The power of locality also compounds two techniques I mentioned, deterministic sorting and identity repartition. Third is composable design. Lastly, locality constrains the downstream design. So sometimes the best practice is not the best practice, is in the locality sensitive system. Right, thank you so much. I'll happy to take any questions.
Cool.